Here is a diagram showing again in a cross section uh, uh, the cochlea with the inner hair cells and outer hair cells, the tectorial membrane and the basilar membrane. But also shown in this diagram is the structure that we call the stria vascularis. The stria vascularis is this collection of epithelial cells which is highly vascularized. And the main function of the stria vascularis is the production of the endolymph. Endolymph is a fluid which is quite similar to the regular extracellular fluid, with the difference that's very rich in potassium, very low in sodium, and the potassium levels is about 150 millimolar here in the endolymph, and this high potassium levels in this chamber creates this potential inside of this chamber, which baths the hair bundle of the hair cells of about plus 85 millivolts. This stria vascularis actually is composed of a series of epithelial cells that will transport potassium from the regular extracellular fluid, in this case we call perilymph, from the perilymph all the way to the endolymph. There's potassium channels and transporters will ultimately drive the production and the extrusion of potassium to the endolymph at very, very high levels that creates this very positive potential that we call endocochlear potential, and the high levels of potassium that can reach 150 millimolar in the endolymph. So the transduction current is carried mainly by potassium. About 7% of the currents is carried by potassium. So when these mechanotransduction channels open in the stereocilia, it allows the influx of potassium into the cells, and also a considerable fraction of the current is also carried by calcium. Again, the endolymph is very positive and very high, rich in potassium. So most of the current carried by mechanotransduction channels is carried by potassium ions. What's the implication on where the energy expenditure is on the cochlea? Speculate why this is the case. Now the interesting question here is how the movement of stereocilia is coupled to the opening of these mechanotransduction channels. Some clues about the mechanism came when people start to realize that the stereocilia or the hair bundle is connected to each other via this very peculiar structure that they call the tippellinks. And the tippellinks, the molecular structure is shown here, and it's basically composed of cell adhesion molecules, and which are connected to various types of myosin molecules. And the myosin molecules attach to actin bundles that you find inside of the stereocilia. Those mechanotransduction channels, as we discussed before, is located on the apical end of those stereocilia, and of this. And what you can see here is another evidence for this localization of these mechanotransduction channels. Here is shown intracellular calcium measurements using a confocal microscope and showing here the calcium levels at the different levels of the hair bundle. And what you can see is that the calcium rise very quickly and very prominently at the apical end of the hair bundle, and much slower and much less in the basal part of the hair bundle. This uh, localization of the hair cells on the top of the stereocilia of each stereocilia, and the existence of the tip lengths and the configuration of the stereocilia from the shortest in one side and the longest in another side led to propose a proposal of this gate spring model, in which a movement of stereocilia towards the longest stereocilia will lead to the stretching of these tip lengths, which will somehow lead to the opening of these channels, while a movement in the opposite direction would lead to the relaxation of these tip lengths, which will lead to the closing of these channels. So when the short cilia move in the direction of the tall cilia, the tip lengths or in this case called transduction lengths, are stretched, and that leads to the opening of these channels, and that provides excitation of these cells. While when there's the opposite direction, when the tall cilia move in the direction of the short cilia, the transduction lengths are compressed, and compression of the tip lengths will lead to channel closing, which will lead to the inhibition of these cells. And the flow of these positive ions, which in this case is potassium, is called the receptor current, and the receptor current here will lead to the release of a neurotransmitter that will evoke action potentials on these nerve cells. Because there are so very few mechanotransduction channels in hair cells, perhaps only one in each stereocilia, and there's very few hair cells in each cochlea, it has been difficult to identify the molecule that is the mechanotransduction channel. In the previous years, has been proposed that channels like amiloride sensitive sodium channel or TRP channels were somehow involved in this mechanotransduction process, but it turned out to be false. And in the past few years now, the best candidate for mechanotransduction channel are those TMC1 and TMC2, and those are transmembrane channel like for TMC, and they're the best candidates to be the mechanotransduction channel. Some of the evidence that TMC1 and TMC2 are the mechanotransduction channels are that these mRNAs for these channels are selectively expressed in developed hair cells at the onset acquisition of mechanosensitivity of these cells. Also, many mutations of TMC1 cause deafness in both in humans and in mice. In the absence of functional TMC1 and TMC2, by doing knockouts for TMC1 and TMC2, it has been shown the hair cells of the mouse auditory and vestibular system lack mechanosensory responses. And finally, that TMC1 and TMC2 localize at stereocilia tips, as shown here with a mouse, a transgenic mouse, in which TMC1 protein has been fused with cherry, and what's shown here is confocal images, and show here in the outer hair cells that those TMC1 channels are located in the tips of those stereocilia, as expected for a bona fide mechanotransduction channel.